Hey PStat, welcome to section 6.2, transforming and combining random variables. So by the end of this section, you should be able to describe the effect of adding, subtracting a constant, or multiplying or dividing by a constant on the probability distribution of a random variable. This should kind of sound familiar. Calculate the mean and standard deviation of the sum or difference of random variables, and find probabilities involving the sum or difference of independent normal random variables. So this is going to kind of relate back to what we did back in chapter 2. We studied the effects of linear transformation on the shape, center, and variability of distributions of data. So recall that back then we had these rules where adding or subtracting a constant a to each observation. So if we add or subtract some constant a, we add or subtract to the measures of center, but it doesn't change the measures of variability. It just does a shift. It doesn't actually change the spread at all, and it does not change the shape. And that was another important piece I don't mention as much, but it doesn't change the shape in addition to that measure of variability. And then oh, sorry, this got screwed up. There we go. Multiplying or dividing each observation by another positive constant that does affect the measure of center. Multiplying or dividing, it does multiply or divide the measure of center, and then it multiplies or divides the measures of spread, like the standard deviation and interquartile range. It does not change the shape of the distribution still, though. So if I double every number, it moves the center, but it also widens the spread, and it doesn't change the shape. It widens it, but it doesn't change. Like if it was skewed to begin with, it'll still be skewed. If it was bell-shaped to begin with or whatever, it'll still have that same shape. So we're going to apply that basically to random variables, and it reacts pretty much in the exact same way, the ways that you would expect. So let's kind of cruise through this. We got Pete's Jeep tours, where he's making money on the total collected, and he's got his probability distribution of how much money he collects. But let's say Pete has to pay $100 to buy permits, gas, and ferry pass for each day. So if we change a new variable v to represent the amount of profit Pete collects, it actually drops down from starting at 300, 450, and so on. Now we're up to 200, 350, and so on. Basically, we subtracted 100 off those numbers. Probabilities are the same. Notice that if we graph this, the shape is the same for this distribution. Just, I guess it'll help better once I show them next to each other. It's just kind of centered, so exact same shape, just centered at a different spot. Before, kind of our peak was at 600, now it's at 500 because we've subtracted 100. Here's actually a formula relating those random variables. If C is the random amount collected, subtract 100 from that, a constant, not a random variable, right? Subtracting a constant. Then we have this new variable v, and how does that distribution compare? So we're interested in how does the distribution of v compare to that of c. Well, we could actually go through and calculate all of these same values. Remember the expected value from last unit, we do 200 times 0.15 plus 350 times that, and so on. So we can calculate our new mean for this distribution. So the mean for v ends up being 462.50 if you do what I just said, and when that happens to be, if you look at it, exactly 100 less than our mean of this distribution. Ultimately, not shocking. And then the standard deviation, if you do it, so if you do 200 minus this new mean, 462.50 squared times its probability, and go through calculating that standard deviation, turns out, well, this 200 is 100 less, this 462 is 100 less, so those differences aren't actually any different. So the spread is no different. The standard deviation is the exact same as it was before if you go through and do those calculations. So the shape as well is the exact same. So center changes if we subtract or add a constant, but spread and shape do not. So just to kind of sum it up, the effect of adding or subtracting a constant, if we add a, it affects the measures of center and location, so like quartiles and things like that, percentiles, all those things do move. As you move this thing, you shift it around, but it doesn't affect measures of variability, and it does not change the shape of the distribution. So Note that adding or subtracting a constant affects the distribution of a quantitative variable and the probability distribution of a random variable in the exact same way. So, as an example for this, in a large introductory statistics class, the score X of a randomly selected student on a test worth 50 points can be modeled by a normal distribution with a mean of 35 and a standard deviation of 5. So this is a distribution that we've got for it. They're saying it's normal, which really normal is continuous, and I imagine this teacher isn't actually doing a continuous assignment of points. I'm guessing they just, you could get a 35 or a 36, not a 35.3 to, whatever. But it's probably approximately normal is probably the better thing to say. But they don't want to get caught up in semantics like I am. Due to a difficult question on the test, the professor decides to add 5 points to each student's score. They're curving. And so this is kind of similar to what I do, only, like I said, mine's a little more complex with a multiplication and an addition. So let Y be the scaled test score of the randomly selected student. Describe the shape, center, and variability of the probability distribution of Y. Well, the shape, if I add 5 to every student, still going to be normal. The center is going to go up 5 from 35 to 40, and the spread is going to stay the exact same. And so that's what we'll see with that. We don't actually have to go through and adjust everybody's score and recalculate, and so that's kind of similar how I can curve test scores. Though I do multiply to affect spread. I don't want to always just leave the spread the same. So that's why I do that. All right, so summarizing, kind of same stuff. Multiplying affects the measures of center and location, affects the spread, but doesn't affect the shape. And so it's basically the exact same as when we did this on distributions of quantitative data. So, an example of multiplying by a constant. El Dorado Community College considers a student to be full-time if he or she is taking between 12 and 18 units. So we got units here. The number of units X that a randomly selected El Dorado Community College full-time student is taking in the fall semester has the following distribution. So we've got some students taking 12, 13, 14, so on and so forth. So this is basically a relative frequency, but we're calling it a probability here because, we're saying like a randomly selected student. It's the probability they're taking 18 units. Apparently it's 0.15. And they've went ahead and kind of graphed that distribution. We've got X represents the number of units, and those are those outcomes, and these are our probabilities. And the mean, they've already calculated for us. They did 12 times 0.25, 13 times 0.1, and so on, added them all up, and they got a mean of 14.65 right there, the balance point in that distribution. And the standard deviation is 2.056, so they've calculated that for us as well. At El Dorado Community College, the tuition for full-time students is $50 per unit. So if somebody's doing 12 units, you could do 50 times 12 to get what their tuition cost is. So that is, if T equals tuition, we're going to come up with a new random variable called T. It's a transformation of X. X was the number of units they take. We just do 50 times X, where X was the number of units they're taking. So we could go through and recalculate out this table and, find all the stuff to do this, but we can do it just in our heads, basically. What's the shape going to be? The same. What's the new mean going to be? Well, it's going to be the old mean, which was 14.65, times 50. What's the new standard deviation going to be? The old standard deviation times 50. So multiplication affects both, right? It is, going to end up being more spread out, right? Instead of going from 12 to 18 units, we're multiplying each of those by 50. So that range is going to be 50 times as much. And so that is how that affects these random variables.